I'm going to talk about the southwestern Cordillera of North America, primarily the southwestern portion of the United States. Current plate boundary position is here, and the red dots are metamorphic core complex locations. And I'm going to talk about the Cordilleran highlands. That acted as sources of sedimentation both onto the what is now the Colorado Plateau and then also onto the margin. And Shown on the right is a reconstruction of taking into account the history of extension and implications for highlands in southwestern Cordillera of North America during the Paleocene through Oligocene. And this highland had significant gravity potential energy, and with plate motion, boundary condition changes, and uh, the slab rollback, ignimbrite flare-up, volcanism, addition of heat, fluids, the region underwent gravitational collapse. And so I'm going to argue that this high topography, this high paleotopography, was a significant source of the early driving mechanisms behind that extensional collapse. And so on the left is a reconstruction model of the history of extension in what is now the basin and range of Western North America. And they quantified offset amounts and the timing of those offsets. And Ali Bahadori and I took those displacements from that model, treated them in essentially as though they were GPS vectors, and treated the material as a continuum. And from their reconstruction, we inferred a strain rate tensor field, including rotation rates, as a function of time, and then starting with crustal thickness estimates inferred from first scope US array data. We integrated those strain rates back in time to get a paleocrustal thickness, and and with a mantle density field model, we inferred a paleotopography model. So that paleotopography is shown here on the right in the latest Eocene. And so what happened is the East Pacific rise collided with the trench uh, at 30 million, and that set off this extension in southern Arizona, western Arizona, and as the Mendocino Triple Junction migrates to the north, the boundary conditions of Pacific North America become increasingly more important as the San Andreas system develops. And so the early part is driven, we've modeled this as a thin sheet dynamic system. The early part is driven by gravitational energy differences. And then as the system progresses, the Pacific North America relative plate motion becomes a major driver. So we then modeled this in 3D using a boundary condition model from mantle convection inferred from tomography, backward advected inferred what we inferred from tomography a density field, and then backward advected that, and using aspect code we then forward modeled that field to infer temperature and traction field through time. And that field was coupled to a lithosphere model that has this crustal thickness variation built into it. It has the topography built into it. And we used underworld geodynamics for this. a viscoplastic lithosphere with the topography and crustal root. And it's coupled to this time-dependent mantle flow field. That mantle flow field shows a progressive heating with time, and it, it, it the there's a hot mantle material moving inward towards the Colorado Plateau. You can see the progression of volcanism through time as the Southwest Cordillera system is extending and developing. And so we made the argument that this temperature evolution, the boundary condition of both temperature and combined with the gravitational potential energy of the highlands was a major driver. We also used Badlands code, which was coupled to the surface topography model to yield mass redistribution, and we had a climate model from latest Eocene to the present that was computed by Ran Feng, and so this is the landscape evolution model for Southwest Cordillera. Again, this is that highland that I'm talking about. In the north, this has been called the Nevada Plano Highland, and then in the south, the reconstruction yields this pretty narrow mountain belt, which is called the Mogollon Highlands. And these highlands have been inferred based on the presence of rim gravels that are found on the southern Colorado Plateau that were shed from highlands that existed to the south of the Colorado Plateau. So the model shows the importance of this thickened crust with low viscosity, lower crust, gravitational spreading, and extension during this early phase, during latest Eocene through Oligocene, and the presence of paleocanyon networks draining off of the highlands, draining onto the plateau, shedding rim gravels onto the Colorado Plateau. And there's a long-lived northeast draining river system coming off of a drainage divide that is the Mogollon Highlands and the Nevada Plano to the west. So this is a major feature of the model. And at one point, there is a later in Miocene, there's a drainage reversal and eventual Grand Canyon cutting. So others have recognized the importance of this long-lived drainage system coming off of a drainage divide in the southwest. It's called the Bell River system, which drained out into the Saguenay Delta in Labrador Sea region, major river system. And so at least this part of the model with this highland, the Cordilleran Highland, Nevada Plano, and Mogollon Highlands is a important not only geodynamically, but it's important in terms of drainage evolution of this major system. So we also compared the drainage, the sediment supply, again produced by Badlands Code, with macrostrat data. There are misfits to the macrostrat, but there's room for improvement. But overall, it shows this increase in sedimentation around 20 million years ago. And again, this shows the north draining river system and eventually
Bill?
a drainage
Bill?
reversal. Yes.
Oh, you got 10 minutes now, just so you know.
Okay. I'm going to speed ahead. I'm not going to show that drainage evolution, which has the Grand Canyon in. Oh, I grabbed the wrong talk. Now I see. Okay. Well, that's bad. All right. So I'm going to have to, unless I unshare, I just realized I grabbed an older talk. That was a real, all right. That's fine. I'll go with this. So I'm just going to focus then on a second drainage evolution model, which actually does show the Grand Canyon cutting. And what we learned from this um, is that gravitational potential energy differences are important early for driving that extension. But as I stated in the beginning, the relative motion between Pacific and North America was a major driving factor from middle Miocene onward. And there's a key thing that happens in this drainage evolution. So at this point, let's see, where's our clock? We're still in very early Miocene now. We're at 22 million years. The extensional collapse of the Mogollon Highlands is happening, and you're getting a drainage reversal. You're no longer getting drainage onto the Colorado Plateau off of the highlands. Again, this is being driven by gravitational potential energy differences and metamorphic core complex formation. But the opening of the Colorado River extensional corridor causes a major drainage reversal and the development of a Paleo-Colorado River system that down cuts through the western part of the Colorado Plateau and then out into what is now Mojave. And as the Baja Peninsula develops and the Gulf of California opens, the Baja Peninsula moves northward and the Gulf of California opens, that Paleo-Colorado River system eventually makes its way into the Gulf of California in this landscape evolution model. So here it is evolving pretty much into the present day. And so this landscape model, which is a second model, shows the importance of the opening of the Colorado River extensional corridor. And that's driven by Pacific North America relative motion rather than gravitational potential energy differences. And the timing of Colorado River cutting is timed with that opening of the Colorado River extensional corridor at about between 15 and 12 million years ago. And so the model predicts a cutting timed with that base level shift between 15 and 12. And that's early cutting. That's an early prediction. It contrasts with work of group like Carlstrom et al. Or Carlstrom's group, where they think a much younger cutting occurred at around 6 million. So, all right, I'm going to conclude now. So the models that we've run to date predict 3 phases of drainage evolution. Before 30 million, there's topography of the Mogollon Highlands and the Nevada Plano. And these yield northeast to east drainage onto the Colorado Plateau, producing rim gravels. Big southwest drainage into what is called the Sespe Delta area. That's transported northward into, it's now found in the Los Angeles region today. It's transported to the northwest via San Andreas motion. There's a major drainage reversal in the middle Miocene that corresponds with a large increase in sediment flux that I showed, around 20 million. And then final cutting of the Grand Canyon that follows the opening of the Colorado River extensional corridor at around 13 million. So one of the things we're excited about is that geologic observations of drainage evolution and the sedimentary record in general holds promise for constraining the next generation of fully coupled 3D dynamic and climate models. So I'll finish there.
Awesome. Thank you very much, Bill. I think Sasha has a question.
Yeah, that's right. Thanks for this great talk, Bill. It's fascinating to see how this landscape is evolving in these models. I'm curious. You mentioned that you infer that you have the collapse driven by GPE gradients.
Yes.
And at the same time, you have a thin sheet model that is driven by the kinematics of the Macquarie and Wernicke paper. So I'm conceptually, how does that work? You drive it kinematically, but you also infer the driving forces. How do you do that?
Yeah. So the thin sheet the thin sheet model has a kinematic reconstruction that gave us the topography, inferred topography, and inferred crustal thickness. And then we actually ran a thin sheet dynamic model, which is basically vertically integrated 3D force balance. So the vertical integral of vertical stress gives the gravity potential energy. And that gives an effective body force term, or GPE differences. And then we do have velocity boundary conditions. So we had velocity boundary conditions that changed as a function of time. And in that 2019 paper, we found that the GPE differences were a big driver they produce large deviatoric tensional stresses when the GPE was present, but as it collapsed, extended and collapsed, you lose the GPE, and then the relative plate motion became important. When we ran the fully coupled 3D model, we found the same sort of feature, except that in the 3D model, of course, you see differential flow going on. You see flow of the lower crust relative to the upper crust in the vicinity of the root zones. And in particular, you get development of detachment surfaces and the flow of middle crust coming up along those detachment surfaces. And you even form metamorphic core complexes. So those are details that do not come out in the thin sheet model, of course, because it's a vertical average. But the 3D did show the importance of this thickened crustal root in the early part of the phase. So they were consistent. They just, the thin sheet can't give you vertical variations in flow.
Right. Excellent. Thank you.